Hello everyone, my name is Jonathan Tucker, and today I'll be giving a presentation on GNSS, interference, PDOA localization, weighted via nearest neighbors. I'll begin the presentation with some background information on the key technologies that nearest neighbors PDOA, or NNPDOA, relies on. Next, I'll delve into the algorithm development process. I'll transition into looking at the experiment design, results, and finally, our conclusion. The first technology that we need to discuss is the automatic gain control, or AGC. The AGC functions to adjust the gain of the incoming signal so that the amplitude of the incoming signal covers the full range of the receiver ADC. It adjusts the gain based on the ambient noise rather than incoming signal power because the incoming signal is expected to be thermal noise, which means noise is dominant. The AGC drives the ADC to a Gaussian distribution, which is disrupted by RFI. This shows we can detect RFI via the AGC. It was determined that the power of the incoming RFI is inversely proportional to the change in the AGC gain, which is seen in the equation in the bottom right. This plot shows an example of the inversely proportional relationship between AGC response and incoming signal power. Please notice that there are three distinct regions in the plot. The region on the far left is below the thermal noise floor and thus too low to activate the AGC. The region on the far right is the saturated region. The middle region is the linear region, where we derive our proportionality constant that allows us to relate a change in AGC gain to incoming signal power. The next background technology we need to discuss is the PDOA algorithm. Using the gain from the AGC, we can determine the power of the RFI. Comparing the power when the RFI is active to some nominal power level allows us to apply the free space path loss equation to obtain an estimate for how far away the emitter is. Using this distance approximation, we can create circles of possible emitter regions. This figure shows what happens when the geometry of the receivers is ideal and the emitter can be accurately localized. From this, we can build the general intuition that a larger drop in AGC leads to a circle with a smaller radius, i.e., the localization solution, or emitter, is closer to that receiver. Next, let's discuss receiver saturation. Please recall that the right portion in the figure is the saturated region, where the incoming power is too high and the AGC cannot drop any lower. Using the intuition built on the previous PDOA slide, it's not hard to believe that having a saturated receiver where the AGC gain isn't accurately represented leads to an erroneous PDOA result. In general, when the receiver is saturated, it could be extremely close or very far away from the receiver. Now let's delve into the algorithm development process. Here we can see an overview of the fundamental problem that we wanted to solve. Is it possible to leverage a saturated receiver to make PDOA localization more accurate? Then we established the hypothesis that using the nearest neighbors to the saturated receivers, we might be able to provide a better PDOA solution. As for our solution process, first we need to know which receivers are saturated. Then we look at the AGC drop of each of the receivers and use the free space path loss equation to determine a distance estimate from each of these. Next, we weight these estimates by the distance between the non-saturated receivers and the midpoint between the saturated ones. This process adds error to the overall localization solution and increases the search area, but by extending the non-saturated solution circles by this distance, we're guaranteeing that the jammer is somewhere within the new solution circle. We can make this guarantee because we're starting with non-saturated receivers that have an accurately quantified AGC drop. So we already know that their solution circles should have the emitter on their border. When we add the midpoint distance, we thus extend the circle to contain the emitter. The important point here is that we're able to take into account the saturated receivers using this range extension. Because we have non-saturated receivers, it's reasonable to believe that the emitter is closest to the saturated ones. However, we can't fully trust the circles obtained from the free space path loss equation using the saturated AGC, so we add error to each of the receivers to create a more reliable solution polygon. Continuing with the algorithm development process, please first take a look at the figure below. Notice the positions of the receiver's emitter in the solution polygon in blue. The solution area within the polygon needs to be discretized. From there, we can minimize the error between the expected power drop and the calculated power drop at each location in the solution polygon for each receiver. We use the constraints that the error should be 0 for non-saturated receivers and could be greater than or equal to 0 for saturated ones. We do this to not only further account for the saturated receivers, but also the error we added before. Now let's talk about how we tested the algorithm. Beginning with experimental setup, through an educational partnership with Edwards Air Force Base, we were able to collect data when several receivers were being jammed by multiple waveforms. These included continuous wave and broadband noise. Both were broadcasted over the L1 and L2 bands. This figure shows the configuration of the jammers and emitters. In total, there were 7 test segments. As you can see, the terrain is varying, which brings up an important point. NNPDOA doesn't take into account antenna pattern or terrain masking. This slide shows 6 of the 7 test segments. The first was a jammer calibration period. You can see that from the experiment, we obtained a variety of ways to test the localization power of our NNPDOA algorithm. So let's see how NNPDOA performed. Here's a results overview showing the AGC over time and how each receiver was impacted by the emitters. We chose to use 3 of the 7 test segments indicated here as segments 2, 4, and 7. We have targeted these segments because each yields 1 or more receiver under saturation. To give you an idea of what occurred during the experiment, first the emitter activates. After emitter activation, there is an AGC response. Note that the node in purple came under saturation. This final figure shows the solution polygon in dark blue, the PDOA over time in black, the final PDOA in light blue, and the NNPDOA solution in pink. This is a more quantified view of the results and includes a comparison between PDOA and NNPDOA. The overall highlights are that there was 1 receiver under saturation. The RFI was emitting a CW signal across the L1 band, and that NNPDOA provided a 150% improvement on the straight line distance between the true jammer location and the localized location. Again, to give you an idea of what occurred during the experiment, the emitter activates. After activation, there's an AGC response. Please note that in this segment, there are 2 nodes that are under saturation. This final figure shows the solution polygon again in dark blue, the PDOA over time in black, the final PDOA in light blue, and the NNPDOA solution in pink with the true jammer position in yellow. The results breakdown for this segment is as follows. There were 2 receivers under saturation. The RFI source was emitting a broadband noise signal across the L1 and L2 bands, and the NNPDOA provided a 50% improvement on the straight line distance between the true jammer location and the localized solution. Again, the emitter activates. There's an AGC response, and please note that in this segment there was only 1 node that came under saturation. And finally, we have our solution polygon in dark blue, the final PDOA solution in light blue, and the NNPDOA solution in pink, with the jammer true position in yellow. The highlights from this test segment are that we saw 1 receiver under saturation, an RFI source emitting a CW signal across both the L1 and L2 bands, and in this scenario, NNPDOA provides a 12.5% improvement on the straight line distance. The main difference between segment 7 and segment 2 is that the RFI emitter is broadcasting on L1 and L2. Also, it's possible that the receivers aren't completely saturated, but are within the saturation region. To conclude, recall that the fundamental question that we were attempting to answer is it possible to leverage a saturated receiver to make PDOA localization more accurate? Through the experimental results, we have proven that the NNPDOA algorithm can improve upon localization accuracy, and in the worst case scenario, provide a solution close in accuracy to the traditional PDOA algorithm.